get that out of the way. Okay, so two types of reactions that I want to talk about today. One is called a single displacement reaction. The other one's called a double displacement reaction. These are not really exciting like our decomposition and our combustion reactions. I'm not even going to bother doing a demonstration of it because we're going to be doing a lab for these two reactions tomorrow, okay? This lesson is actually quite short. There is more details to single and double displacement reactions that you're going to learn in grade 11, but right now I'm just introducing you to a single displacement and a double displacement reaction. So the lesson's quite short, and then I'm going to give you some time to work on some homework. But what I will also suggest to do instead of just working on the homework is I've already put the posting up for tomorrow's lab, and the hypothesis, and it's not a formal report, but the hypothesis is to complete balanced chemical equations for the reactions that we're going to do, and you can do them ahead. So in other words, at the end of today's class, you can work on the lab's hypothesis, and then tomorrow all we have to do is get the observations and do some questions, all right? So you'll be able to do those hypotheses ahead of time so that, you've got that out of the way. And if you didn't get them done ahead of the time, you can do them whenever you're going to get done and whenever they're due, but you're going to be able to do that. Okay, so a single displacement reaction. I'm going to bring this whole thing up here. Again, I'm not a fan of the animations, so we'll just bring that up and get that out of the way. And I'm going to let you just write that down, and then we will talk about it. All right, I wasn't going to do a demonstration, but I think I can show you one really quickly, a little one here as you're writing. Okay, so single displacement, a single displacement reaction involves the reaction of an element with a compound. The element displaces an element that's in the compound, and a new element and new compound are produced. So it's essentially a trading places type scenario. Here I have element A, again, a general formula. We'll put it on our chart here in a moment. It's reacting with a compound BC, and going to bring down the periodic table. You can see here that I have, if A is a metal, then I'm going to get B, and then I'm going to get AC. All right? Now, if A is a metal, why does it displace B instead of C? If A is a metal, why does it displace B instead of C? In other words, down here it says it's a non-metal, and A went into C's position. You see here, BC, it kicked it out, it went into C's position. So C is left by itself and BA is formed. So if A is a metal, why does it displace B? What is it about a chemical compound that has it displace B instead of C if A is a metal? What do we know about ionic compounds and the way we write it down? Yep. The metal is always first. So when we have something like sodium chloride, the metal always comes first. So if A is a metal, it replaces the metal. And if A is a non-metal, it will replace the non-metal. All right? It will replace the element of its own type. All right? Now, many teachers use all kinds of analogies to help students remember. You can, and the one that some teachers will use is, in this case, is something like a dance. So let's say the elements are at a dance, and B and C are dancing away, and element A feels that particular element would like to dance as well, and that element cuts into the dance. Taps B on the shoulder. Excuse me, may I cut in? B steps aside, and A takes its position, and then B is all on its own. All right? Now, if we were to analyze this reaction in far more detail, like we do in grade 11, you will learn it's nothing like a dance. It's nothing like a dance in an actual reaction vessel. But when you look at the chemical reaction, it looks as if A is simply cutting in and taking the place of B and displacing it. So for now, that's a good way of thinking of it. Let's take a look at what that looks like. I wasn't going to do a demonstration, but I do have all of the apparatus. Do you want me to use like retro goggles like in the video? These won't stay on my face. Okay, anyway, they'll work. All right, so I have all the apparatus ready for our lab tomorrow. So I've simply grabbed some of the solutions that we have there. This is silver nitrate, all right? And I'm going to put some copper with this. So what I was doing earlier on, I was stripping the plastic off of a copper wire. So I'm going to put some copper in with some silver nitrate. All right, for those who are watching the video, I'm just writing copper and silver nitrate on the board. Well, what is going to be produced for this single displacement reaction? What is the copper going to do, and what's going to be left? What are my products going to be for this single displacement reaction? Pausing for understanding, and then a hand raising. Ashley thinks she knows, but she's not going to put up her hand. She refuses to. Who's going to do it? Garrett, what do you got? Silver and copper nitrate. Now, copper is one of those that has more than one charge. It turns out that the form of copper that forms is copper 2 nitrate. Let's see if that happens. Notice that the copper is nice and shiny, all right? And it's nice and clean. And now we're going to put it in some silver nitrate. So first, in order to kind of give it a little bit of a structure, I'm going to wrap it around a pen here just to kind of make a shape. I just want to coil it up so I can get as much of the copper into my little test tube as possible. And I've got such a tiny test tube, I really got to make that coil smaller than the pen. So now I'm just kind of twisting it up, and I'm trying to see if I can get it to fit into the test tube. Success, fit in the test tube. And now I'm going to take some of the silver nitrate, And these are the dropper bottles we're going to use tomorrow. It's got silver nitrate in there. Silver nitrate is actually a colorless, transparent liquid, but it's not very stable. So what happens is, as I leave it in this jug, the silver itself becomes silver metal for some of the silver nitrate. It sticks to the side, and it's turning the inside of my container like a little silver mirror. But there's also silver nitrate solution in here, and it is a colorless, transparent liquid. You'll be able to see that when I put it in here. So let's put some in here. So you can see, even though this looks like it's silvery and gray, the liquid itself is colorless and transparent. But there's silver nitrate in here. It's dissolved. It's a dissolved form of silver. Let's put the copper in there, and you might think, bam, instantaneously we should get a whole bunch of silver, but it does take some time. But this is fairly strong stuff because I can already see that the silver is a little gray. Can you see that gray all of a sudden starting to form? See how at the top it's nice and shiny and copper color, but down underneath the surface it's a little bit gray at this point. And it almost looks fuzzy. Can you see that it's looking a little bit fuzzy from back there? I'll bring it around here in a moment after I let it react a little bit. What's happening is the silver is being deposited onto the surface of the copper, because as it touches it, the silver is going to stick to it, and the copper is going to go into the solution, and it's going to dissolve. There's one other way for us to tell that this chemical reaction is happening. It turns out that copper 2 nitrate is blue, all right? Copper 2 ions are blue. How do you remember that? Copper 2 is blue. I see it rhymes, right? That's how I always remember. So if we leave this long enough, if enough copper goes into the solution, we should see it turn blue. Let's keep going with the lesson, and we'll come back and look at that later on at the end of the class. Again, like I said, single displacement reactions are not exciting. This is not explosive. It's not going to blow up, but it is happening right there. Okay, let's do some examples. Click. So go ahead and you can write out that, and you can write out what you think goes in the blanks. And I have a feeling you guys have the ability to fill that in. I will take it up in a moment, but you should be able to figure that out. Magnesium and hydrogen chloride. What are we going to get? What's going to go by itself? And what's going to be the new compound? Ashley, what do you got? Magnesium and hydrogen chloride, what's going to be? Hydrogen and magnesium chloride, excellent. So what did magnesium take the place of? Hydrogen. Magnesium displaced the hydrogen. Now, hydrogen is a non-metal, but it sometimes behaves as a metal, especially when it comes first in the name. All right? Hydrogen's a gas. If I did this reaction, it would bubble away. It would make a bubbles. Bubbles would come out instead of a solid being formed. All right? So there we would see bubbles being produced in this particular reaction. Chlorine and sodium bromide. Now be careful with this one. Chlorine is a non-metal. So what's it going to displace? What's going to go by itself? What's going to be the compound? So chlorine is the non-metal this time. This was a metal right here. That was a metal. So we displaced the first guy. This is a non-metal. Products. What are we going to get? Boss, what do you think? Sodium by itself? In this case, no. And that's because chlorine is the non-metal, so it's going to displace also the non-metal. So what do you want to put there? Yeah, bromide, and actually it turns into bromine, all right? And what's the new compound going to be formed? Sodium chloride. Sodium chloride. So because chlorine is the non-metal, all right, it's going to displace the non-metal. Because magnesium is the metal, it's going to displace the metal, all right? So they'll swap out positions. So the chlorine took the place of the bromide because non-metals displace non-metals. Click. Let's look at, how many more have I got here? I'm just looking ahead at my examples. It's okay. Here, let's look at this one in terms of a chemical reaction instead of a word equation. Again, hydrogen is first. Even though it is a non-metal, it is in the position of the metal. Hydrogen has the ability to behave as a metal if it loses an electron, but it also has the ability to behave as a non-metal. And in this case, because it's first, it's behaving as a metal. Zinc is definitely a metal. I don't know where my voice is going. A metal. Let me work on that. So, metal. All right. What are we going to get? Some products. Josie, what are we getting here? Hydrogen plus zinc chloride. Now, we've got to be careful when we do this. We have to use our knowledge of chemical formulas to get this right. Hydrogen by itself is a gas, and it counts as one of those Hofbrinkel gases. So what do I have to do to make that more correct with the hydrogen? I need H2. H2. And zinc. Zinc has a particular charge. So we would need our periodic tables. You guys don't have it, so I'm going to take a look for you. Zinc has a charge of 2. So when we cross over the charges to get the formula, we have to use our chemical formula rules. Chloride is -1. Zinc is +2. So what do I need to make my formula for the zinc chloride more correct? Josie? A 2 after the chloride, ZnCl2. So when you do a chemical reaction, you've got to use your knowledge of chemical formulas in order to get the proper formulas. Now, in order to do this right, we should balance it. What do I need to put to balance this reaction? Yep, Tom? HCl, a 2 in front of the HCl. So 1 zinc, 2 H's, 2 H's, 2 Cl's. Very good. Okay? So that brings together kind of all of our skills in determining that one. The zinc took the place of the hydrogen, all right, because it was working as a metal. Okay, let's do just a couple of examples here. Let's do those 2 examples, then we'll move on to the double displacement. Let's do the word equation and the balanced chemical equation. So if we're doing the balanced chemical equation, we need our periodic tables so we can get formulas. And if you have your periodic tables, if you've made a printout, that's awesome. Again, if you're a slacker, well, hey, that's the way it goes. You're a slacker. Slacker? All right. Oh, you're not a slacker. Nice. Yeah, you're a slacker. Again, I'm recording all this, so I'm gonna make note that everyone knows in the universe that Tom is a slacker and that Josie is a slacker.
Oh, Taylor's not a slacker.
Oh, Taylor's not a slacker. Nice. Martina, are you a slacker? Say it out loud so your parents can hear you. Say that you're a slacker. Oh, you're not a slacker. Nice job. Ooh, nice. 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 Oh, no, not so nice. All right. Okay, so let's do the word equation first. What's the word equation going to be for this guy? What's going to be the products? You tell me the products. What are the products going to be for this? Silver, and copper nitrate. That's the one I'm just doing on the board. That's perfect. Copper, and I'll tell you that it's going to be copper 2 nitrate. Because you need to know which copper it's going to be. Let's do the formulas for this. Copper is Cu, all by itself. It's an element. It's not Hofbrinkel, which means it doesn't get a 2 or anything like that. It's just Cu. Silver nitrate. Go ahead. AgNO3. Do I need to cross anything over? No, it's 1 and 1, right? Ag is 1. Nitrate, when you check up on your chart, is 1. You don't need to cross anything over there. Well, you do. It's 1 and 1. You just don't write anything down. Silver is Ag. Now I need a copper 2 nitrate. I need a copper 2 nitrate. Again, copper, Cu. Nitrate, we've already used. NO3. The question is, do I have to cross anything over? Taylor, what do I need there? 2 after the nitrate, so I need some brackets as well, right? Brackets 2. Excellent. Let's balance it. I'm likely going to leave Cu and Ag for last. The nitrates are staying together, so I might as well balance the nitrates. What do I need? Tom likes to balance, I think. Tom, go ahead. Balance away. 2 silver nitrate. What else? 2 in front of the silver. Nice. And that's it. We're good. All right? You guys, I'm looking at the time. I want to get to the double displacement. This is technically also copper 2 chloride. All right? I'm not going to do the balanced chemical equation for this next one. I want to do one that has a non-metal that I'll do a balanced chemical equation for. Then we'll move on to double displacement. But many of you have already wrote this down. What are the products going to be here? Iron is a metal. So what are the products going to be? Aaliyah, what do you think? Iron's a metal, so what's it going to kick out? It'll kick out copper. So copper is going to be by itself. Copper. What's going to be left? What's the other product, Aaliyah? Iron chloride. Iron has more than one option. Actually, let me show you the trick that I use to tell which one it is. Take a look at the 2 charges for iron. Can you see what the 2 possible charges are? Do you notice that one of them is in bold? Can you see that one of them is in bold on that table? The bold one is the most common one, 3. So you'll likely get 3 in this reaction. Iron, 3, chloride. Leave some space. You can go ahead and balance that at a later date, maybe for some practice if you're preparing for our quiz, maybe at the end of the week. But I want to jump ahead and I want to do one which has a non-metal and let's do the fluorine and the potassium chloride. Now I'm going to have to write my products underneath here because I don't have enough space on my whiteboard, so I'll put the products underneath. Fluorine. What's the fluorine going to displace? Thank you, Thomas. Thomas gets it, and then he gets excited, and he starts verbalizing everything, which means no one else gets to play. The fluoride is going to be displaced, and it's going to become fluorine because it's going to lose its "ide"-ness, its charge. It's going to lose its charge. What's going to be left? Someone other than Thomas. Martina, what's going to be left? Potassium, sorry? What was the second part? I couldn't hear you. Potassium chloride? That's not correct because that's what I started with. And the fluorine kicked out the... Look at what I did. Did anybody see what I did there? Bzz, bzz. Who did this? Did you do this? Did you say fluorine? I'm blaming this on Tom. I am straight up. It was Tom. Tom messes me up every day. What's the product now? Fluoride. Thank you. Potassium fluoride. Balanced chemical equation. Formula for fluorine. F2. 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 Correct. It's one of the Hofbrinkel gases. Correct. Good job, Thomas. That makes up for that earlier screw up that screwed me up. That wasn't me. Potassium chloride. Someone else. Tom, just have a break there, man. Jeepers. Julia, formula for potassium chloride. KCl, 1 and 1. Done, right? KCl. KCl. Products. Chlorine. Chlorine. Bo, what do you think? Yeah, it does. Cl2. Has to have a 2. Cl2. And potassium fluoride. Bailey, what do you think? Potassium fluoride. Formula? Okay, F. Potassium has a charge of 1, right? Fluoride has a charge of 1. We don't need the 2. We don't need the 2. Now we got to balance it. Yep. The potassium, which one? Fluoride. You want a 2 here? 2 in front of the potassium chloride. Good. Good job. Good work. Okay. Those are single displacement reactions. Let's now talk about double displacement reactions. Does that concern you?
Yeah.
Why?
Yeah, I love it. That's nice.
Well, you can figure it out. You're smart.
No. I don't even know what the end of the thing was.
Use your word equation.
I can do a word equation.
What do you have?
I just wrote the letters.
So you've got F2 plus 2KCl to
Yeah.
produce
Oh.
Cl2, and you can't figure out what that missing piece is?
Yeah.
Well, I can't help you then. Your brain should be able to figure out what the missing part is. Double displacement reactions involve 2 compounds, and in this case, simply they trade partners, right? Metal goes to the other non-metal, and that one switches back. And so you can see here we've got compound AB reacting with compound CD to produce then AD. A was the metal, so the A goes into that metal position. All right? So it swaps out the C. Again, if we want an analogy to help us kind of remember this, instead of someone cutting into the dance, excuse me, may I cut in? You can think of a dance, those dances, I remember back in the 80s, I think it was grade 7 or 8, say to your teacher, hey, can we have a party? In the classroom. Everybody has parties in the classroom, right? No? They still do that in the 2000s? They say, hey, can we have a dance? Right? And we would bring our records. Yeah, and this was, like I said, this was mid-'80s. So there was an Olivia Newton-John album that just came out with a very controversial song. It was called Let's Get Physical. Have you ever heard of it? Yes, correct. I went to a Catholic school. We started to play this. The teacher lost his mind. It was awesome. It was absolutely hilarious. Anyway, if you think back to those types of interactions, the teacher would make sure that everyone was having a good time so that certain people wouldn't dance with other people because that would make people sad. So what did they do? They would have a snowball dance. You know what I'm talking about? Yeah. Snowball. What happens at snowball when they say snowball? Oh, that's good. What happens when they say snowball? Okay, everyone, snowball. You got to switch partners so everyone's happy that you're not sad that you're not dancing with a particular person. So snowball, everyone trade partners. No? Never heard of such a thing? All right. Is this count as a snowball dance? No? Doesn't at all? Like, come on, you react to two things? Okay, ions, snowball, get new partners. That's not what's happening up there? What are you going to say? This is being recorded. Keep that in mind. It doesn't matter. You can think of it either way, right? The metal gets a new non-metal partner, and whoever's left, they get the other partner. So you're right. You can think of it as the non-metal switching as well. Either way will get you the correct answer. You just swap the metal out, or you can swap the non-metal out. It makes no difference. It's not an issue. Okay, let's do some examples of this. Now, I'm not going to do any actual chemical examples of this to demonstrate. These reactions are typically indicated by precipitation reactions. So sometimes you'll get a new precipitate and you'll see that precipitate come out. Sometimes a gas is produced, so you might get some bubbles, right, that come out of that particular thing. What was? Yes, I did. I did tell you the answers, correct. Yeah, so they're just examples where I gave you the answers. Did you want to figure them out? Is that no fun? Okay, well, maybe I have some other examples where you have to figure it out. Let me just take a look ahead here. You just keep writing and we'll see if we can accommodate you with some. No, I don't. That's just I've given you the easy ones. Hide them and scratch them out. They're there. They're there. I can't scratch them out. They're there. Okay, let's write this down, folks. Actually, technically, this would be lead. Oh, goodness. What's the most common oxidation state of lead? 2. This would be lead 2. Look at Ashley's mad because she doesn't have a challenge. So let's do the balanced chemical equation for that first one, just so Ashley can feel as if she's accomplished something here. So when you write down the word equation for that first one, we'll also try to, in a moment, do a balanced chemical equation for that as well. Is that challenge enough for you? Is that good? Good. Do you write anything down back there, Thomas? Do you write anything down back there? Oh, does he? All right. Okay. So I like your intensity and involvement, but eventually you're going to have to go back and study something. And if you have nothing written down, I don't know what you're going to go back and study. That's my question. Have we got the first one written down? We're good to go? Hey, let's finish this off so I can let you have some work. Lead 2 nitrate. What's the formula going to be? Lead 2 nitrate. Pb, NO3, and 2. Why is it a 2? The lead is 2 and the nitrate is 1. They cross over. All right? The lead is 2, the nitrate is 1, and it crosses over. Okay? Potassium iodide. Okay, Thomas, just dial it back a little bit. Dial it back. Logan, potassium iodide. It's not a P. That would be a phosphorus. Ki. 1 and 1. Ki, 1 and 1. Lead 2 iodide. What would its formula be? Yep. PbI2. And potassium nitrate. Potassium nitrate. For the nitrates you're checking up there. Oh, you got to do some quizzes for me someday. That's exciting. Do it tomorrow? Okay. Yeah, we'll do it at the beginning while they're getting ready for their labs, or maybe even at the end. It's okay. We'll get it taken care of. What do we have for potassium nitrate? Who's got it? Potassium nitrate. What do you got? KNO3. Let's balance it up. What do I need to balance this? What do I need to balance? All of the polyatomic ions are staying together, so the nitrate stays together, so we can do it with the nitrates. Logan, what do you think? What am I going to put and where? Just tell me what and where. There's some 2's in there. We got to take care of some 2's. Yep, go ahead. 2 in front of the potassium iodide to take care of the iodides. A 2 in front of the potassium nitrate takes care of the nitrates and takes care of the K's. I think we're done. Let's balance this last one just to do a little more balancing practice. Let's balance the last one. Yeah. Oh, no, I want an answer. Josie, what's your question? Yes, it can. It doesn't matter the order in which you write them down. So now balance it, Josie. To balance the OHs. It's okay. It's done. It's done. I don't know. It's balanced. Right? There's 2 NAs, right? 2 NAs. There's 1 sulfate and 1 sulfate. That would do it. Okay. Let's not write this stuff down. Let's just talk this through. Identify this as a single displacement or a double displacement. What is A? Single displacement. 1 reacting with the compound. B, what reaction we got here? It's a double displacement. Yep, we've got a compound and it's producing 2 new compounds. Excellent. And again, just given the reactants, tell me whether it's single or double. What's this one here? Yeah, it's double, compound and compound. We're not going to complete. We've done a bunch of that. A single element with a compound. Okay? All right, we're getting there. And I'm going to finish that summary. And we're not doing that. I just want you to go to the homework. Yeah, we get the idea. We've done this. There is the homework down there. Boom. No, it isn't. No. Okay. So I am going to stop the video here as you guys are writing that down. I need my keyboard. Stop.